question is, there are 5 conformations drawn as a given prediction. And then what we do, we rank these conformations, we actually rank this conformation by the stability, right? This is a stable conformation. I mean, that's kind of drawings out. They're a little bit away from each other, but that actually meant as an eclipse conformation. Because if you really draw on top of each other, it's going to be illegible. So that's an eclipse conformations. That looks stable, that looks eclipse, that looks stable, right? Something that you got to keep in mind is all the eclipse conformation have a higher energy than stable conformation, right? So eclipse conformation are those two, but they're a bit different. If you look at what are close together in space, if you look at that one, you got the methyl on top of the methyl, right? And then on the other side, hydrogen on top of the ethyl groups. Ethyl is bigger than methyl, so it has a bigger presence there, but that's on top of a hydrogen. You got to keep in mind that. On the other side, this eclipse conformation, you got the methyl on top of hydrogen, and then methyl on top. I mean, the methyl be right behind the ethyl group. So this is not really the biggest concern here because hydrogen is a small. So whatever things on top, this is an alkyl chain, that's an alkyl chain, but methyl and methyl on hydrogen is probably not the one that raises the energy too much. What raises the energy is a permanent substituents. If you look at that one, methyl on methyl, this one, you got ethyl on methyl. The difference is ethyl groups has a 2 carbon. It's a bigger, right? It should be twice bigger. I mean, in space, it could be more than twice bigger, it could be more things. But it's much bigger than the methyl groups. And as I told you earlier, the steric hindrance is basically the body and the helium touching another body. So when they get bigger, they feel more steric hindrance. So that's the what raises energy. So if I'm asking you, between these 2 eclipse conformations, which one will be the least stable, then which one would you choose? 2 small one, I mean the relatively small one on top of each other, or the bigger one on top of each other? I mean, methyls are not small compared to previous here. So that is the kind of the things you need to do. I mean, these are eclipse, but this eclipse conformation is worse than that one because you got the bigger substituents on top of another one. So because of that, I would say because stability goes 1 more stable, 5 least stable, this will be the least stable one here. And then this will be the right next one. Then there are 3 stable conformation, right? Those 3 stable conformation is going to be better than the eclipse anyway. So we got to figure out which one's the best one, which one's the second best one, which one's one after. For that, we need to look at where the biggest substituents in the relative position. So look at this one. This one's a methyl and methyl, they're right next to each other. And then we just talked about that is a quotient, right? 2 big substituents. They're not on top of each other because it's stable, but they're not really on opposite side. They are 60 degrees apart. That's a quotient conformation right there. And then this methyl and that ethyl, that's also quotient too. So this one is 2 quotient interactions. And each quotient kind of weighs up the energy about 1 kilocalorie. Let's talk about that. This particular one, this H3 doesn't have a gauge, no gauge there because this is hydrogen, that's hydrogen, so this is fine. And then the other CH3 is a white behind below, so that's anti, right? But there's an ethyl groups here. This ethyl groups has a methyl right next to each other, so that's a 1 gauge interaction right here. There's 1 gauge interaction. If you look at that one, this one, you got the methyl opposite side of the ethyl groups. So this is truly the anti-conformation of this. And then ethyls are fine because the hydrogens are in the neighborhood. But the 2 methyl groups are right next to each other, 60 degrees apart. That's a 1 gauge interaction. So this one is a 1 gauge interaction. That is a 1 gauge interaction. This one is a 2 gauge interactions. So that's what I'm trying to show you here. having a gauge relationship will raise up energy, small amount, but it raises up energy, like a kilocalorie. This one is a 2. That is just 1. This one is a 1. So which one will be number 3? That should be this one, right? Because that is a more number of gauge interaction compared to 2. So now the question is, which one is the most stable conformation out of those 2? Right? When these are methyl and ethyl, right? As I said, when the size gets bigger, even though they're 60 degree apart, things can get closer, even a little bit higher than this. So the smaller things in gauge is better than the bigger one in gauge. So that's the reason this one gets number 1, the most stable conformation here. There's a second most stable conformation, and the third most stable conformation goes down, and then all the Krebs conformation becomes 0.5.